Hello, everyone. We're actually going to be starting a new unit. We're starting to talk about the periodic table. So if I ask everyone, make sure you have your periodic table ready right now. And let's get our notes going. Sorry. Okay. So how did the modern periodic table get to be the way it is? Because the modern periodic table actually wasn't always this way. This is our founding, I guess, father of the modern periodic table is what we can call him. He's considered the father of the modern periodic table. And he first organized the periodic table in 1870 using Dalton's atomic model. He first organized the periodic table. Back then, he was basing all of his information off of Dalton's atomic model. Remember that Dalton's atomic model was the plum pudding model? I'm sorry, not the plum pudding model, the billiard ball model. So we have to remember that he thought that all atoms were just made out of themselves. A gold atom was simply a very, very, very small little sphere of gold, and so on and so forth. So he was kind of using these ideas of whole atoms, and he didn't really know anything about subatomic particles. So if we look at his periodic table, we can see here for his periodic table that he did a special thing, and he was the first, and the reason we give him credit is he was the first to organize it in two different ways. And the first way that he organized it, he lined them up in terms of mass and increasing mass. So we can see here that he put hydrogen. Oop, I want to get my highlighter, my laser pointer. You can see here he had hydrogen, and then he had lithium, beryllium, boron, carbon, nitrogen, oxygen, right? So he lined them up in terms of increasing atomic mass. But what he did is that he did these things called octaves or groups of 8. So he said that if for whatever reason, if you're starting at helium and then going across, if you stop at 8 and then you start over again, you start seeing some very interesting trends. And they call it the law of octaves, that when you do that, you get these groups down here that have a lot of similar characteristics. And if you look at your periodic table, the modern periodic table, we can tell that lithium, sodium, potassium, rubidium, cesium, they are all in the same group on the modern periodic table. So he was the first one to kind of figure that out. And that's how our modern periodic table, that's why it's organized in such an interesting, I dare say, weird way. But the coolest thing is that not only did he find he found these groups that had interesting similarities to them, but he was actually able to predict to a very close degree, to pretty good accuracy, atomic mass of unknown elements. For example, if we look all the way over at group 7, group 7 is right here, right? This group 7, if we look at it, we see fluorine and chlorine. Magnesium didn't really fit, but bromine, something, and then this J, and that J is 127. If you look at iodine, iodine happens to have a mass of 127. So he was actually able to predict unfound elements, unknown elements, and their atomic masses. So he predicted the existence of iodine before we even found it. Of course, nowadays, that is not how we line up the periodic table. Nowadays, we don't organize it by atomic mass, we organize it by increasing atomic number, right? Atomic number 1, atomic number 2, 3, 4, 5, 6, 7, 8. Okay. Now, unfortunately, you got to memorize a couple of the elements here. Just because you need to know symbol to name, it's going to help you a lot. So here are some names that I want you to know, some symbols and names. Okay, so mercury, antimony, potassium, sodium, iron, lead, gold, silver, tungsten, kind of not so much, but the first couple definitely have to know them. And the reason that some of the names are different than the symbols is because they come from the original Greek or Latin words. For example, potassium, elemental symbol K, comes from the original, I believe it's a Greek word, kalium. Actually, I think that sounds more Latin to me. Iron comes from ferrium. Uh, Mercury comes from hydrygium, Hydrgyum. Gold, Au, is for orium, and silver, Ag, is for argentium. Tungsten actually originally did not come from Latin. It came from, I believe it was more Germanic, or either Germanic or more Eastern European. It was called Wolfsbane, something like that. Something about wolves. Now I can't remember it, but had to do with the fact that tungsten did something that is similar to how wolves act. So unfortunately, you got to memorize these. Sorry. But talking about the periodic table and how it's arranged, we said that it's arranged increased of atomic number. That's how we increase it, but it's also arranged into columns and rows, and we have very special names for those columns and rows. So from the top to the bottom, we have these things called groups. So that would be considered group 1. And then we have group 2, group 3, group 4, group 5. So the group names can be found up here, right? There would be group 2, 3, 4, 5, 6. And the reason we put elements in the same group, now Mr. Mendeleev didn't know that, but elements in the same group all actually have similar chemical properties. So all of the elements in group 1 have very similar chemical properties. All of the elements in group 2, very similar chemical properties. So that's a really cool thing there. Now, that's from top to bottom. Going from left to right, and we're going to start with lithium, we call these a period. So this whole row here, that's one period. So that would be period 2. So how it works, here's period 1, period 2, period 3, period 4, period 5, period 6, period 7, period 8, period 9, period 10, and so on and so forth. Now, we say that period number typically means the occupied shell number. In other words, the first period only has one occupied shell, not subshell, shell. The second period only has 2 occupied shells. The third period only has 3 occupied shells. Now, things get a little bit more complicated when we start getting into atoms that have electrons in the D and the F shell, because as we saw, things are really weird with the D and the F shell, right? Energy levels are changing and it doesn't make sense as much, but period number, and there are some more patterns we can get. Now, there are some very special groups that get special what we call family names, and they are referred to by these family names. So the first group, that group 1, those are the alkali metals. Group 2, we call the alkaline earth metals. Group 3 through 12, that's one big family called the transition metals. Group 17, we call the halogens. And group 18, we call the noble gases. They're called noble gases simply because they tend to not chemically react. They tend to be chemically inert. So we call them noble because they don't deal with the riffraff of the rest of the periodic table. They don't bond with it. So these are also names that you should know, be familiar with, I would say memorize. Please note that hydrogen is an alkali metal. I'm sorry, an alkali element. It is not an alkali metal. Hydrogen is not a metal. Okay, now this next slide isn't going to make sense because it didn't finish it, but there are 2 more groups, and this is on your periodic table, and I apologize for this one, but you're not going to be able to see it. I want to point out the actinides and the lanthanides. This is just a picture of your periodic table with a blue box on it, but those 2 groups down there, they're actually periods. They get the lanthanide and the actinide. Now, where does lanthanide and actinide come from? It comes from element number 57 and element number 89. Element number 57 is lanthanum, and element number 89 is actinium. So please note that the periodic table actually gets pulled back. So where we see groups 3 and 4 over here, 3 is actually here, 4 is actually supposed to be way over here. So this whole group right here, group 4, should actually start after 103 and whatever's above it, right? And we'll talk more about that in class, but those are called the lanthanides and the actinides down there. Now, there are also 3 major groups of elements, more than the groups. I guess 3 major categories. This doesn't have to do with group number or period number, but 3 major categories of elements. And the first major category is the metals. So most of the elements on the periodic table are metals. Metals lose electrons to become ions. All metals, they always lose electrons to become ions. And general properties of metals are they are malleable, meaning that they are bendable and flatten into sheets. They are generally solid at room temperature. Mercury is a liquid at room temperature. Gallium has a very, very high melting point. I'm sorry, a very low melting point. And depending on how you define room temperature, it's sometimes a liquid, sometimes a solid. So I think, and you can look this up, I think 25 degrees Celsius, gallium would be a solid, but above 25, it would be a liquid. So look that up, but mercury definitely. Ductile metals can be made into wires. You can stretch them out, right? All wires are generally made out of copper. And the reason that we make them into wires, not only because they're ductile, but also they are good electrical conductors. They're actually good both thermal and electrical conductors. Thermal, of course, being heat. And metals in general have a high luster. They're very shiny. So that's our first major category. Second major category, we have our nonmetals. And nonmetals tend to gain electrons to become ions. Why am I writing the word tend? Well, it's because while metals always lose electrons, nonmetals don't. For example, noble gases, if they're not chemically reacting, that means that they're not really turning into ions at all. Also, there are many nonmetals that can become both positive and negative. But overall, nonmetals tend to gain electrons to become ions. They tend to become negative ions. Other properties of nonmetals: brittle, opposite of malleable. You can't bend them nor flatten them. Many of ours are liquid at room temperature. Many of them, Hg was from before. So we can just, let's cross that one out. Shoo. Don't worry about that. The noble gases are gases, obviously, at room temperature. A lot of them are electrical and thermal insulators, which is super important, right? We make our windows out of glass because they allow light in and they keep heat inside. They don't allow heat outside. Glass is made out, well, I guess glass is technically more non-metal than, glass is more complicated than that, but there's a reason that we use thermal insulators, nonmetals, to keep things hot because they keep the heat in. They have low luster. They tend to be not very shiny, right? Carbon is not very shiny. Sulfur is not very shiny. Third major category of elements, and this is the confusing one. It actually has 2 names. They're called metals, or semi-metals or metalloids. And the reason we call them that is because they have properties that are both metallic and non-metallic. They both lose and gain electrons. Now, here's the thing. It's not like they're half and half. It's actually more like they're on a spectrum, in that some elements are more metallic, some elements are less metallic in the semi-metals, but they're super important. For example, silicon is a semiconductor of electricity. And because of that property, we make all of our computer chips out of silicon. Now, Another thing for you to memorize. You do have to memorize all of the metalloids, the semimetals, okay? And the reason we memorize them is because they form what is called the staircase. So here is the staircase on your periodic table. Sorry. And the reason we have the staircase, we're going to say that we'll call the metalloids blue ones. So the metalloids will be the blue ones. Okay, come on. There we go. So the metalloids are the blue ones, but the cool thing is that we can tell where the metals and the non-metalloids based on our periodic table and this staircase. Anything to the left of the staircase is considered a metal. So, and the only exception there is hydrogen is a non-metal. So all this here, this is all metals. Metals, 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 metals. And then down here, these are also all metals. So to the left of the staircase are metals, and then anything to the right of the staircase, we make them green, are our nonmetals, and the only exception to that rule is hydrogen. Hydrogen is a nonmetal, so all of these are nonmetals. So you should, and that's why we memorize where the staircase is, because you should be able to tell me if something's metallic or non-metallic down here. I'm going to put this there, and then I'm going to throw livermorium. Technically, it's a metal. The naming scheme, ium, is for metals. And that is your introduction to the periodic table. Congratulations, we have made it. Yay! Of course, we want to keep that. And thank you so much. I hope everyone has an excellent day. Bye.